So I'm going to talk a little bit about gravity duals to gauge mediation. And so the outline for my talk, which I hope is not too long, I'm actually worried it might be too short. So first, I'm going to briefly review the general formalism for gauge mediation as well as the holographic gauge formulation. In describing this holographic formulation, I'm going to have this intermediate 5-dimensional effective field theory that I'm going to use and discuss. And then using this, I'm going to calculate these current correlators. Those of you who are familiar with general gauge mediation will know why this is important. If not, I'll briefly describe why they are, and then I'll conclude. So first of all, I mean, I don't have time to justify why we want to think about SUSY. I assume all of you know. But just to orient ourselves, I'm going to briefly review the minimal scenario for gauge mediation. In this scenario, we have some visible sector, say the MSSM or some extension of it. Then there's also some SUSY breaking sector in which SUSY is spontaneously or dynamically broken by, for example, a non-vanishing F term. This sector communicates to a so-called messenger sector via superpotential interactions, at least in the minimal scenario. And then kind of the important feature is that the visible sector communicates by gauge interactions to this messenger sector. And in this framework, soft terms in the visible sector arise from quantum effects. So for example, this is the famous, one of the diagrams that gives a gaugino mass. So here's a gaugino. This is some, excuse me, this is the scalar partner of some messenger field, and this is the fermionic partner. However, more generally, I mean, this simple picture won't, well, there are more general things I can do, I should say. And so instead of dividing things nicely into these two boxes, you can put everything together into some so-called hidden sector. And then what kind of differentiates gauge mediation from everything else, this is the definition by Seiberg, Mead, and Shi, is that as the visible sector coupling goes to 0, these two sectors decouple, and the visible sector remains supersymmetric. So in this framework, a quantity that's very, very useful is this current superfield. So this is a field that's built completely out of hidden sector fields. It has the usual vector component, which is conserved. It has some fermionic partner and also some scalar partner. And it couples to the visible sector in kind of the supersymmetric generalization of things that we're familiar with. So in the non-supersymmetric case, this describes the interaction between the two sectors. And then supersymmetrically, there's interaction with the visible sector gaugino and the visible sector D term. And it all, of course, depends on the visible sector coupling. So the 2-point functions of this current superfield, they result in visible sector soft terms. Or rather, I can express the visible sector soft terms in terms of this guy. One supersymmetry is broken somewhere in the hidden sector. So there's some scalar component. The 2-point for this guy is parameterized by some function C0. Similarly, there are functions describing the fermion and the current correlators, or the vector-vector correlators. There's some Lorentz structure here that I'm suppressing. There are also some delta functions that I'm suppressing. Really, what's important is that these are characterized by these different functions. There's also another current correlator for the spinors, in which now these are both of the same representation. And again, there's some Lorentz structure that I'm suppressing. And actually, there's a factor m here, where m is some characteristic mass scale. And then in the case when supersymmetry is present in the system, when it's not spontaneously broken, all these C's have to be equal to one another, and this B must be vanishing. And as a result, or not as a result, but one way to see this is that the visible sector gaugino mass is proportional to B1 half evaluated at 0 momentum. And this fermion masses kind of go as this integration over all of these guys. These factors of 3 and 4 just arise from the numbers of degrees of freedom in the vector and spinor components. Okay. So this is all the framework of general gauge mediation by these guys. So in general, the hidden sector might be strongly coupled, and I can't calculate these in any sort of direct way. However, one of the things that ADS-CFT was essentially born to do was to calculate these 2-point functions. So ADS-CFT, or more generally gauge gravity duality, gives us a way to calculate these guys. And here basically what I'm doing is, instead of this picture, I'm going to replace this hidden block, this black box, with a warped throat. And then probably should combine these two slides. So when G visits is equal to 0, then the visible sector gauge group is a flavor group of the hidden sector. And then the dictionary between the gravity side and the gauge theory side for some in this picture. So the hidden sector is realized by the entire warp geometry. The famous example that they use is Klebanov-Straussler. The visible sector gauge group, which in this limit is again a flavor group of the hidden sector, is realized by some D7s that kind of fall a little bit into the throat. J mu, this is the hidden sector current that couples to the visible sector, vector. This is dual to the vector field living on the D7 brane. And the non-supersymmetric state is dual to the addition of anti-D3 branes, which I represented by this little pink dot here. And this star is to remind me that actually the back reaction of these is a subtle issue, and someone will talk more about it tomorrow. So ADS-CFT tells us schematically that if I have some operator O in the field theory that's dual to some field phi in the gravity side, then if I want to calculate this two-point function, I basically calculate somehow like this classical correlation on the gravity side. So here, the appropriate gravity side action. So remember, I'm interested in the correlators for fields that are dual to D7 fields. The appropriate action comes from the dBi and Chern-Simons action for the D7 brane. Then, to maintain calculability, what I'm going to do in this presentation is I'm going to model the hidden sector in some like very ridiculously simple way, which I'm going to model it by ADS5 cross S5, at least before the addition of anti-D3 branes. So you should really interpret this as definitely a toy model. And I'll talk a little bit about some of the drawbacks of doing this in a moment. Furthermore, I'm going to model the visible sector gauge group by a U1, but this is somehow not a major complication. This is just for simplicity of notation. Okay. So in order to calculate these two-point functions, it turns out to be useful to have some five-dimensional effective field theory. And there are two ways that I'm going to go about doing this. One way is that, well, these D7s are going to wrap some S3 in the setup that I have here. And the dimensional reduction of this theory is pretty straightforward. When you do so, you get some five-dimensional action that has some kinetic terms. They're actually non-canonical kinetic terms. There's some function in here in general that I haven't written down. There's, of course, a mass for the gaugino. There's a mass for a scalar that corresponds to the transverse deformations of the 7 brane. There's also this kind of weird coupling here that vanishes in the pure ADS case. So this is after integrating out all the other modes. I mean, there's a huge power of modes coming from, for example, the Wilson lines, and those are more massive. And all these parameters, the mass, this parameter here, and this mass, that should be an m squared, obviously, and this function here, which I should have written down, they depend on the warping of the background, the fluxes, and the distance from the D7 brane from essentially the center of warping. And in general, these are radially dependent. So in the case when I'm evaluating this action on a purely ADS background, and I let the ADS go, the D7 brane go all the way to the bottom, then these become constants. And for example, the mass saturates the BF bound. And in the case of a supersymmetric background, the theory that I write down here exhibits n equals 1 in 5 dimensions. And I guess just to remind you, this multiplet consists of a 5D vector, a Dirac spinner, and then some scalar field, which is right here. So as I mentioned, the hidden sector current is dual to the gauge field that lives on the D7 brane, where the legs of the D7 of this gauge field are all on the external directions. Similarly, the spinner component of the current superfield is dual to one of the components of the D7 brane gaugino. This is actually at this point a choice which component I make. So what about J? What about this other scalar here? So kind of what's maybe, at least was a little confusing to me, is this J is somehow dual to this off-shell field. So what we can do is in flat space and flat 5-dimensional space, the Maxwell theory I can write it off-shell in terms of an SU2R triplet of auxiliary fields. So n5 equals 1 exhibits some SU2R symmetry, and there's an auxiliary field that transforms into 3. And then I can take this theory and I can write it in 4-dimensional superspace. I at least learned these from these papers. It's possible it may be elsewhere. So when I do this, I write this in terms of one chiral superfield. This is supposed to be one chiral in n equals 1 in 4 dimensions, and one vector superfield. And the auxiliary component of this vector field is related to one of the auxiliary components here, and also a derivative of the scalar. And since this is an n equals 2 theory, n equals 2 in 4 dimensions, there's some choice of where I can bend the n equals 1 that I'm really interested in. And then kind of an arbitrary choice that I make is that I embed this n equals 4 by making the identification that this vector superfield is dual to the current superfield that I'm interested in. This is one of the ways in which this is toy. I mean, more realistically, I'd want some hidden sector that exhibited n equals or only had 4 supercharges. So that was in the flat space case. Wow. So when I want to go into warp space, what I can do is basically warp the fermionic coordinates of superspace. Here the warp factor is defined in this way for ADS. D7, or the auxiliary field, is similarly modified. So it was this before, and now some warp factor appears here. Rho is some radial coordinates. They work this out for the ADS case, but it works more generally for any supersymmetric case. And when you integrate out x3, which is easy to do, this turns out to be the dual to J. So it's essentially sigma, that scalar field that I mentioned here, but it carries like a derivative and some warp factors and some other rho factor. So now I want to prepare the state. This is prepared by back reaction of anti-D3 branes. Really what's important here is the warp factors and the 5-form flux up here. And all these, the differences from the ADS case are proportional to the relative number of antibranes that I add. For a space that's asymptotically anti-de Sitter, which is like this, it turns out that the scalar field always has a solution of this form, which might be a little different from what you're used to. That's because it saturates the BF bound. And then just by plugging things in, you can find in asymptotically ADS spaces, D takes this form. So here, this leading term is identified the source. The subleading term is the response. And then I can determine the response as a function of the source by imposing some infrared boundary conditions. Then to actually calculate the correlators, you go through the process of holographic renormalization, for example. For want of time, I'm just going to kind of skip through. And then the important thing is that this 2-point function is essentially the derivative of this response as a function of the source, and then you evaluate it when the source is 0. This is the basic ADS CFT. So in ADS, the result is well known. The solutions for sigma are Bessel functions. For DS, the solutions are hypergeometric functions, and the scalar coordinates I can write in terms of digamma functions, which I can expand. Something looks like this plus some finite terms. For D7s and ADS plus anti-D3 branes, I can't solve this exactly, but I can expand in terms of hypergeometric functions, these guys. I can find ZNL and ML to leading order in S for any L that I want. Actually, it turns out to be just rational functions or rational numbers. So I can do similar steps for other fields. Obviously, I don't have time to talk about it since I don't have time to talk about this one. But one can easily check that in the supersymmetric case, all these guys are equal to one another. B, which was one of the other fermion correlators, vanished. However, for the non-supersymmetric case, when the number of anti-D3 branes is not 0, these guys are not different. B, however, is still 0, which is one of the other ways in which this is very toy. And then I can use the formalism of general gauge mediation and arrive at this expression for the fermion mass, where C is approximately 90. And unfortunately, because B is vanishing, it turns out that the gaugino mass is also vanishing. Okay. So I'm essentially out of time, so I'm just going to leave this concluding slide up there.
Well, thank you very much. Are there any questions?
Yes.
So B equals 0 in the sector, even in the presence of the anti-D3. That is because of the large asymptote.
Yeah. Or another way to see it directly from the D7, for example, is there's no 3-form flux. But of course, if we had any 3-form flux, it would also break the R symmetry.
Okay. So do you expect that once we, for example, take a Coulomb structure plus
then that B should absolutely be not. I mean, that's what we found, right? When we
what we did.
We did it in a different language, but yeah. Yeah.
Other questions? If not, that's